Thanks.
Okay, yes, so this was a little bit on short notice. Was not scheduled for the afternoon, so the slides are freshly made for you over the lunch break. So if there are typos in there, just tell me afterwards. Okay, so in the morning we talked about white dwarfs as the stars that supposedly explode as type 1a supernovae. And we modeled this as thermonuclear explosions in these white dwarfs. And for that, of course, we needed to know the basic properties of white dwarf matter. So this is what we discussed in the morning. We need to know the equation of state in order to model the explosions. But what we also, of course, need is we need to model the dynamics of the explosion. And this is what I will talk about in the afternoon today. So this is a lecture about reactive fluid dynamics. Probably some of you already know fluid dynamics quite well, others maybe don't. So I will start again from the basics and explain actually what the equations of fluid dynamics, how they are derived and what they actually mean. And then we will specify the ingredients we additionally need in order to use them to model thermonuclear explosions of white dwarfs. Okay, so this is it's not the first lecture, I forgot to set up the new number here, but anyway, so this is the lecture on computational, on reactive fluid dynamics. So I will start out discussing general balance laws, and then I will, starting out from that, discuss the other equations of fluid dynamics, and then we will take a look at the source terms that we need in order to not only model fluid dynamics, but reactive fluid dynamics and fluid dynamics with all the other ingredients that we need in order to capture the phenomena that are at work in the thermonuclear explosions of white dwarfs. So this is reactions, of course, but also transport processes, as we will see. All right, so reactive fluid dynamics. So in principle, fluid dynamics is a good approach to astrophysical problems, to modeling astrophysical objects. We have, in principle, different choices, but since astrophysical objects are macroscopic and so large objects and complex objects, it's quite often useful to describe them in terms of effective theories. And for thermonuclear supernovae, this is also the case. So we use the equation of state for white dwarf matter that was derived from concepts of statistical physics, but the modeling of the explosion process now takes a look at matter on larger scales. So we actually use here the concepts of fluid dynamics and thermodynamics. So this is different from classical stellar modeling, of course, classical stellar evolution modeling, where one usually takes approaches in terms of hydrostatic models. So here we have fluid dynamics or hydrodynamics models. This is because in the explosions, of course, we have to deal with dynamical phenomena that take place on the dynamic time scale of the system. All right, so the concept of fluid dynamics in principle also derives from the concepts of statistical physics in a rigorous way. I will not follow this approach here, so you can actually find this in textbooks, but rather take a less fundamental and less rigorous approach. So I will start out from a macroscopic picture in a phenomenological picture, and then derive the equations of fluid dynamics from a description of matter as a continuum. So this is actually done because it's shorter, because it's more instructive, and also because this is actually the fundamental concept that is behind a numerical implementation of fluid dynamics. So also you, in this numerical treatment of fluid dynamics, you usually follow the concepts of balance laws and treating matter as a continuum. And this is something we will discuss tomorrow. Now, the lecture will again be a Blackboard lecture, so this is the second Blackboard lecture and the last one I have, because I want to here discuss some more fundamental concepts. So the phenomenological approach to deriving the equations of fluid dynamics is in the spirit of the physics of continua. So the underlying idea here is then that one applies the idea of conservation laws or balance equations to hydrodynamical quantities. Now, in general, a balance law is expressed as here. So we take a look at, we consider an extensive hydrodynamical quantity A, inside a volume V that is assumed to be fixed in space. And then, of course, this hydrodynamical quantity A inside that volume V can change with time by two effects, namely that we have a flow of that quantity over the surface of the volume, or that we have a production or destruction of that quantity inside the volume. So these are these two terms here. The change of the hydrodynamical quantity A with time is due to flow of that quantity over the surface, or production and destruction of this quantity inside the volume. So this actually is what we would call the integral form of a balance equation. We can actually, from that, make the transition to the more commonly used differential form. If we define instead from our hydrodynamic quantity a density as here, so that we get by integrating that density over that volume our quantity A. A similar thing can then be done for flux density, so that is the flow of that quantity A over the surface of our volume dV. So this can be expressed again in terms of a density, namely the flux density. So here we integrate over the surface of the volume the flux density JA, and this actually then describes the temporal change of our quantity inside the volume due to fluxes over the surface. And formally, we can actually also do the same thing for production and destruction of our quantity inside the volume, and this gives us a source density S of A of production or depletion of our quantity inside the volume as here. So we again integrate over the volume over source density, and this describes then production and destruction of A. Okay, so we insert these densities into our integral form of the balance equation. So this is just done here. So this is the temporal change of A, now expressed in terms of the integral over the density. And this is then equal to the two terms on the right-hand side, the flow of the quantity over the surface, here integrated over the surface with the flux density, and the integrated source density inside the volume that gives us the production and destruction of the quantity inside the volume. Of course, you can then apply the divergence theorem to the first term here on the right-hand side, and then express also the flux in terms of a volume integral of the divergence of that flux density. Now, since the volume over which we integrate here can be chosen arbitrarily, we can leave out this integration, so the integrands should also fulfill the same equation, and this gives us then the differential form of the balance equation as here. So this is the usual differential form of the balance equation. So we have the time derivative of the density is given by the minus the gradient. The minus here is actually a convention that we have positive and negative directions going out and inwards of the volume. So the temporal change of the density is given by the divergence of the flux density plus the source density. Okay, now this can be applied to fluid dynamics. If we want to describe the flow of an ideal fluid, that means a flow of material that's non-viscous without the complications of diffusive transport and reactions for the moment, then we base our description on three fundamental physical principles, namely conservation of mass, momentum, and energy. Of course, this is a non-relativistic treatment where mass and energy are separately conserved. These physical principles of conservation of mass, momentum, and energy are then represented by the balance between convective transport and source terms in terms of such balance equations. So if, for mass, of course, we don't have any sources or sinks in the non-relativistic treatment. So that means we have strict conservation here. There are no source terms, and that means that our balance law as applied to mass with the mass density rho looks as here. So this is the temporal change of the mass density is given by the divergence of the mass flux density, which is just the density, mass density times the velocity of the fluid. Momentum conservation Of course, here we do have source terms due to pressure forces and external forces, and this gives rise to the additional terms we have here, the gradient of pressure, and here on the right-hand side we have a two-force term that is due to an external force. Finally, energy conservation. This is usually expressed in terms of the specific total energy density defined as here, so that we have the total energy density is the specific kinetic energy plus the internal energy density divided by density, mass density, so that we get the specific, that means per mass energy. And with that, we can write down a balance equation for the energy as well. Again, those terms appear here due to external forces. So these are the Euler equations of fluid dynamics. That's a set of 5 partial differential equations, and these describe the hydrodynamics of an ideal fluid. Of course, they cannot be solved as they stand here, because we still need to close them with an equation of state that relates the energy to the density and the pressure. We discussed this morning how we can describe Y12 matter in terms of an equation of state. Okay, so this is ideal fluid dynamics. Non-ideal fluids, of course, behave differently. So the Euler equations, as stated on the last slide, apply only to non-viscous fluids. They do not allow to describe the more general viscous flows, where the mean free path of particles cannot be considered small. So that means that we have a transport of energy and momentum through the fluid by diffusion of particles in configuration space. So this can be treated. We can generalize the equations, the Euler equations of fluid dynamics, to the Navier-Stokes equations. So this is done by generalizing the pressure scalar that we had in our Euler equations to the stress tensor here, which is composed of the scalar pressure plus the viscous stress tensor. And here's one form of the viscous stress tensor for Newtonian fluids, where we have coefficients in here that describe bulk viscosity and dynamic shear viscosity. So viscosity effects then enter here in this pressure term. Okay, so that of course changes momentum balance. Instead of the gradient of the pressure here on the right-hand side, we have now the divergence of the of our stress tensor pi. Okay, so this then is the Navier-Stokes equation. Of course, energy balance also changes because we had a pressure term there before, so this has to be modified as well. And then we have a general description of viscous fluids in terms of the Navier-Stokes equations. Now, with that, we can actually estimate the relevance of viscous effects for the dynamics of the fluid. And this is actually usually expressed in terms of the Reynolds number. So the Reynolds number is defined as the ratio of the magnitude of the inertial forces term and the magnitude of the viscous forces. So if we take a look at this equation here, we have two terms here, except for, of course, the external force term. We have the advection term, so that is the divergence of the momentum flux density, and we have the divergence of the stress tensor. So this actually includes the viscous effects, and this here is just pure advection. And this is what we want to compare. And as you see in the momentum equation, the advection term is nonlinear. So this is what actually makes hydrodynamics interesting, this nonlinearity in the advection term. And in the Reynolds number, we compare these two terms, the magnitude of the inertial forces in terms of the advection term to the magnitude of the viscous forces. So we can actually just take these two terms and assign typical scales for all the quantities that appear here, and this defines then the Reynolds number. So the Reynolds number here, this is the advection term, density times velocity squared over a length scale squared, and the other term is then the viscosity term, and this defines our Reynolds number with a typical velocity scale V here and a characteristic length scale L, and mu here denoting the dynamic viscosity of the fluid. Okay, so for astrophysical objects, usually we have very large scales, of course, and we have large velocities. So these, of course, enter the scales, and the velocities enter our Reynolds numbers. So this actually would have us expect very large Reynolds numbers if we have large velocities and large scales. And astrophysical fluids usually have rather normal viscosities, so they are not extraordinarily large. So therefore, for typical astrophysical situations, we find that the Reynolds numbers are very large, on the order of 10 to the 10 or higher. So that means that viscous effects are usually subdominant for dynamical processes. So therefore, in most cases, astrophysical fluids can be regarded as ideal, non-viscous, and can be modeled with a simplified set of the Euler equations. Now, even if this was not the case, even if viscosity was not non-negligible in the physical situation, we quite often have the situation that the numerical schemes that we then use to solve for hydrodynamics by discretization errors introduce a numerical viscosity. And this numerical viscosity is in any case much, much higher because of the limited resolution that we have in numerical simulations. Is much, much higher than the original physical viscosity. So therefore, it does not make much sense to put in an explicit model for the physical viscosity, because if you then do numerical simulations, this will be dominated by numerical effects anyway. Now, another significance of the Reynolds number, of course, is that it actually tells us something about turbulence. So I already talked about this a little bit. So we actually, in the Reynolds number, compare two terms of the Navier-Stokes equation. So one is the advection term, the nonlinear term, and the other is the viscosity term. So the nonlinear term is actually what creates all the interesting phenomena, makes the solution of the equations of fluid dynamics such a challenging task. So this is responsible for turbulence. So that means that if the Reynolds number is large, and that means that the magnitude of our advection term is much larger than the viscosity effects, that means that then we can expect turbulence. So we have turbulent flows in the regime where the Reynolds numbers are very large. And this is usually the case in astrophysical situations, and as we will discuss tomorrow, this is very important in thermonuclear supernova explosions where we have to deal with turbulence. So many cases, these turbulent properties of the fluid may drive the dynamics. So this is the case in thermonuclear supernovae. But this, of course, then poses additional challenges to the numerical simulation of astrophysical objects because of the high numerical viscosity. We will not be able to actually reach the Reynolds numbers in our numerical simulations that are characteristic for the astrophysical situation. So as I said before, we have typical Reynolds numbers in the astrophysical fluid of 10 to the 10 or 10 to the 14 even, and with numerical simulations one can reach at best something like 10 to the 4 or so. Okay, now the equations that we discussed so far, the Euler equations, just describe pure fluid flow. If we actually leave out the right-hand sides, if we leave out external forces, then we have the homogeneous equations, and these describe pure fluid flow. On the right-hand side, we can add source terms, and they actually take into account additional physical effects. Relevant source terms that need to be accounted for thermonuclear supernovae are gravity, of course, then nuclear reactions, and transport processes. Of course, you can think of many other physical effects that can also play a role, such as magnetic fields, or general relativity effects and so on. So you could actually come up with a long list of additional effects that you want to also model with hydrodynamics. But for the case of thermonuclear supernovae, these are usually left out. Gravity is well described in the Newtonian approach. The magnetic fields of white dwarfs are usually so low that the energy in the magnetic fields is orders of magnitude lower than all the other energy scales, so therefore one would expect these to not be dynamically relevant, although there have been also some claims that at some place they may actually modify turbulence and so on, so that's not completely excluded, but this is usually not taken into account in current models of thermonuclear supernovae. Okay, so let's discuss these source terms and start out with gravity. Of course, the most important external force is self-gravity of stellar objects. For a Chandrasekhar mass white dwarf, we have, as we discussed in this morning, a mass of about 1.4 solar masses. The radius of such a Chandrasekhar mass white dwarf, if we integrate the hydrostatic equilibrium equations of that, we find the radius, and this is something like 2,000 kilometers or so. So that tells us that Newton's gravity constant times the mass divided by the radius times c squared as a measure of GR effects is rather small, so this is 10 to the minus 3. So that tells us that GR effects can be safely neglected when we deal with white dwarfs, or if we deal, if we want to model the thermonuclear supernova, thermonuclear explosions of white dwarfs. So for these purposes, it is enough to use a Newtonian treatment of gravity. So that means that the source term that we have on the right-hand side of our equations of fluid dynamics, maybe I can show this again. So the source terms in the Euler equation, so we have here on the right-hand side these source terms due to external forces, the momentum equation, density times the external specific external force, and here also in the energy equation we have an external force term, and the specific external force F, of course, is to be modeled, and for self-gravity we take a Newtonian treatment. So this source term is then just given by minus the gradient of the Newtonian gravitational potential. And this gravitational potential, of course, can be determined in principle from Poisson's equation, as you all know it. Okay, so the next effect that we want to include, of course, if we want to model thermonuclear explosions, is nuclear reactions. So nuclear reactions, of course, take place if the density and temperature are sufficiently high. And this is in particular in the supernovae the case. And here a large number of different types of reactions is usually involved. These are grouped according to the number of participants in the interactions as one-body reactions. So this would be beta decays, electron captures, and photon disintegrations. Then we can have fusions between two nuclei. These are two-body reactions, and even three-body reactions. The notation for this is that we introduce this lambda j as denoting the reaction rate for one-body reactions. Then this bracket notation for the thermally average cross sections and relative velocities in the center of mass system for the two-body reactions, and we do the same thing for the three-body reactions as well. And then we can actually write down the expressions for the changes of the composition. Okay, so I think here a slide is missing, so I was a bit too fast in preparing the slides over the lunch break. So I thought now we would actually have the nuclear networks here. So this is actually something, so there's something wrong with the order of the slides. I apologize for this. Anyway, so nuclear reactions will then introduce composition changes, of course, and these composition changes of the material is something that we want to account for, and this in principle could be followed in terms of number densities for each of the species. So Ni is then the number densities of the nuclear species I. The disadvantage of following these reactions and the composition changes in terms of the number densities is that we have Ni changing due to reactions and mixing, but also due to volume changes. So that is a quantity, of course, that depends on volume because it's the density, and therefore it is also sensitive to expansion and contraction. So therefore, instead of using number densities, we therefore follow the composition changes in terms of mass fractions as defined here. So the mass fraction is then defined as the number density of species I times the atomic mass number of that species divided by the sum over all the masses that we have in the material. So that, of course, gives rise to the constraint that the sum over all mass fractions of all species should add up to 1. For describing nuclear reactions, however, it is more conventional to not use mass fractions, but quite often it's also the case that one uses the specific abundances, so that means per mass instead. So this is just the mass fraction divided by the mass number, and this gives rise to the specific abundance. Of course, then these should not add up to 1 again, but just the product of the specific abundances with the mass numbers, and if we sum over them, that should actually give 1 as a constraint. Okay, so with that we can express, so here's the nuclear reaction networks that I expected in the last slide. So here we can then express the change of the composition in terms of the change of the specific abundance Yi for species I as here, and we have here on the right hand side the one-body reactions, the two-body reactions, and potential three-body reactions. So this gives us the temporal change Yi dot of each species, so we can write down such an equation for each of the species in our material. And this, of course, changes due to reaction with all other species that are in there. So this, therefore, is a large set of equations. This equation, these terms here on the right-hand side have additional coefficients. Just for completeness, they actually count the number of particles that participate in the reaction, and the factorials that we have in the denominators then prevent double counts, and plus or minus stand for production or depletion or destruction of the species in the reactions. Okay, so this is our nuclear reaction network. It's a set of coupled nonlinear ordinary differential equations. The nonlinearity here is due to the dependence of the reaction rates on second or higher powers of the abundances themselves. Now the problem that one in principle has with solving such reaction networks is the stiffness of the system, and this is due to the vastly different values of the abundances of different species that we have in the matter, and the vastly different values of the reaction rates. So reaction rates, as we will also discuss later on in more detail, for some cases in our situation of thermonuclear supernova explosions, depend on very high powers of temperature, for instance. The nonlinearity of this set of equations, of course, makes an analytic solution virtually impossible, and therefore one has to solve them numerically. So how do we couple these changes due to nuclear reactions to our fluid dynamics system? So in order to keep this a bit more transparent, we rewrite the network equations by abbreviating the right-hand side. So we write the network, the changes of the specific abundances Yi as a function on the right-hand side Fi that depends on density, temperature, and the abundances of all other species. So this is just a shorthand notation for the reaction network. Now, if you want to couple this network to fluid dynamics, of course, two fundamental effects have to be accounted for. And the first is the conversion of nuclear species that changes the composition. And the second effect is, of course, that the reactions will release or consume nuclear energy. So this, of course, should be reflected in our system that we solve. Now, let's take a look at species conversion first. Well, species conversion has, in principle, no directly visible consequences for the Euler equations as we stated them before, because the total mass of the system will not be much affected by nuclear reactions. So we have only very small changes due to changes in the nuclear binding energy, but it will affect the masses only very little. So this is not really what we need to model here. And there are no modifications in the momentum and energy balance obvious from just the species conversion. However, the equation of state does depend on composition of the material, because the mean molecular weight may actually change of the material with nuclear reactions, and this of course affects the equation of state, but it has only an effect on the contribution of the ions of the nuclei to the equation of state, and this is a subdominant effect because pressure and energy are given by the electrons. However, there are reactions that lead to neutralization, so they then change YE, the mean number of electrons per baryon, and of course this has a significant effect on the electron gas component in the equation of state, and so this is something that one needs to account for. Okay, now, I said before, we don't actually see much of a difference if we actually look for species conversion effects in the Euler equations, because the total mass is conserved, but of course the mass of each individual species is not. In order to follow this, of course, we have to then augment the Euler equations as stated before by an additional set of n equations. N is here the number of species we have in the system. So this then specifies the species balance for each of these species in the system in terms of the mass fraction. So this can be written as here as the balance equation again, so same form as we had before for our balance equations. So we again have the change of the species density in terms of an advection term, and we can have a source term, and this source term is of course due to reactions. Now, if we actually write down such a balance equation for each of the species we have in the system, then of course this will overdetermine the equations of fluid dynamics of our system, because we have the constraint that the sum of all equations must be equivalent to mass conservation. That already was our first equations of fluid dynamics. So therefore, we have to obey this constraint on the species conversion rates, so that the sum of all the right-hand sides of the nuclear network has to be 0. So that means that the equations of mass conservation and species balance have to be treated consistently, and the usual practical approach is that one drops one of these species balance equations and instead follows total mass conservation. All right, the second effect, of course, is energy release. So reactions, of course, produce, or if they are endothermic, consume energy, and this, of course, affects energy balance. So this is accounted for by an additional source term on the right-hand side of the balance equation that we write as rho times S. So this is our source term due to reactions, and of course, the quantity S depends on all species conversion rates that we have in our nuclear reaction network, Fi. Okay, so with the mass axis for each species, delta Mi is the mass of that species minus the mass of the constituents individually times c squared, and we can actually then give a number for, or a simple expression for that source term, and this is actually here given in ergs per cubed centimeters per second with the reaction rates here on the right hand side. So this can be then added to the energy equation, and with that additions with mass conservation, species balance, momentum balance, and energy balance, including the source term due to nuclear reactions, we then establish the set of reactive Euler equations. So this then describes hydrodynamics of a reactive flow. Now, in addition to that, of course, the treatment of thermonuclear combustion processes would also require the specification of how heat is transported to propagate the reactions and how species are distributed. So therefore, we, in addition to the reactive Euler equations, have to also include transport terms to the system. And this here is then the set of equations that is derived from the Euler equations of fluid dynamics, but now also includes the source terms due to gravity here as the gradient of the Newtonian potential. Here and here in the momentum and in the energy equation, we have the terms that are due to reactions in the species balance equation and in the energy balance equation. And in addition, we have a term that accounts for species diffusion with VD denoting the diffusion velocity of each species. So this actually enters here in the species balance equation, and it also enters in the energy balance equation. And in addition, in energy balance, I have put in another term that accounts for heat flux. So this then is a rather large system of equations with different effects accounted for: gravity, nuclear reactions, and transport processes, together with a description of fluid dynamics. And this forms the basis of modeling all the processes of combustion that we need to describe thermonuclear explosions of white dwarfs. Of course, one could ask the question, is this list of source terms complete? Is this the full set of equations? And of course, the list here is not exhaustive. In principle, one could also think of adding other effects such as radiative heat flux, but as argued by Timmis and Woosley in 92, this is unimportant white dwarf measure. The most important energy transport effect, of course, is conduction due to the degenerate electrons. Potentially, also one could also think of including dynamical effects due to magnetic fields. This is also not considered here, but I have argued already that the energy in the magnetic fields of typical white dwarfs are so small that they probably are dynamically not very relevant. So therefore, one could argue that the choice of effects that we now have included into our system is actually suitable to model all the effects we're interested in thermonuclear combustion of white dwarfs. All right, so this is already it. I think I would still have like 10 minutes to go, right? So I could start with the next topic, or I don't know. I will not finish the next topic anyway today, so yeah.
So can we ask questions?
Yeah, you can ask questions.
You said we probably don't have to worry about magnetic fields then, but they can change the viscosity. It can be an effective viscosity.
Yeah.
Does that make it better or worse as far as trying to simulate?
Well, I mean, so there was some discussion of whether this has an effect on the smaller scales on turbulence, right? And this could actually be the case, right? So there was the discussion that actually you would actually increase the Kolmogorov scale, so you would actually dissipate the turbulent kinetic energy at larger scales, and this may actually have an effect on down to which scales the flame interacts with turbulent eddies. And so this has been discussed in one paper, but only pointing out the effect, and it was not clear what the consequence of this would be. And so people have not really looked into this in much detail so far.
Any more questions?
So I don't know if this is relevant, but could you consider the white dwarf, is it like just standing still in these models and you model the structure, or is it both?
I mean, the equations that I discussed in this lecture are the equations of hydrodynamics, right? So this is all time dependent. And in this case, I mean, you have, of course, changing configurations. You have flows, right? Hydrodynamical flows. So this is, of course, what we wanted to get at, because in the end we want to model explosions, right? So we don't want to solve the equations, the hydrostatic equations. Of course, in principle, the hydrostatic equation are a special case of these equations, right? If you take a look into momentum balance and you actually set up a situation where gravity is actually compensated by the pressure gradient, then of course the left-hand side, the change of the momentum density will be 0, and then you have the equations of hydrostatic equilibrium. So this is just a special case. But of course, I mean, the practical consequence is also something one should think about. This is a more general problem if you actually want to model stars, not only supernova explosions, but in general stars hydrostatically, right? I mean, then you actually also, for the progenitors of supernovae, you want to set up something that in the beginning, before you ignite reactions, for instance, is in hydrostatic equilibrium. And this is, of course, because hydrostatic equilibrium is a special case of the equations of fluid dynamics, something that should be in the equations. But the question is your numerical scheme good enough to recover this? Or do you actually introduce effects due to discretization errors that make it hard to actually maintain hydrostatic equilibrium? It turns out it's very hard to maintain hydrostatic equilibrium. One of the reasons is that you treat gravity as an external force, whereas pressure is actually something that comes out of the hydrodynamics. And you have a different discretization of pressure and gravity. There may be mismatches, and this is very hard to account for in numerical simulations. So keeping a star in hydrostatic equilibrium for many dynamical timescales, this is very hard. And you need special measures. So there's measures like well balancing that can help to get this under control in numerical simulations, but this is not trivial.
Could you go over just once again the difference between the 1 and 2 and 3 body equations? Or
You mean here? Or further? Okay. Yes. I mean, this is in principle just a way of writing the nuclear reaction network in sort of a transparent way. I mean, you just group these different terms on the right-hand side according to different physical effects. So one is one-body reaction, like beta decays, and then you can have fusion effects that you actually then would have to write down in terms of these thermally averaged cross-sections.
So I have another question on the numerical side. When you have...
We'll discuss numerics tomorrow, but anyway.
Not discussing, but now
Okay.
conduction, heat conduction.
Yes.
You can have numerical heat diffusion.
Mm-hmm.
How big is that in your models? Do you have to worry about that, or is it small compared to the true conduction?
Well, I mean, numerical heat conduction in our numerical simulations, I don't know, actually, no. I think...
It's from that advection term you can get
Yeah.
heat.
I mean, of course, you...
When people did subthermospheric
Yeah.
explosions, because as the shock was moving out around white dwarf, you can get some conduction and some heat diffusion.
Yeah, but that would be also the numerical heat conduction would be very slow compared to the dynamical timescale, the shock propagation timescale, right?
It was in this level, but at least this was a complaint about Elie-Nivny's calculations.
Okay.
It had heat diffusion into the core, and it was causing some, it would diffuse a little bit into the core and then ignite it, and then so he ended up getting...
So we have not seen any such effects in our simulations, but no. Yeah. But of course, I mean, this is also, of course, I mean, as all numerical effects, this is also a matter of resolution that you have in there, right?
Yeah.
And I don't know what simulations you refer to, but if these are old simulations of the 1990s also, it's easily possible that the resolution was not set that high there. Right. Okay.
last question? If not, the size.